Welcome to the poster session. So we will now have a quick fire advertisement for poster flash talk sessions, Pinaki. We'll have a quick fire sort of advertisement for the various posters that are there. They are being put up, and everyone's encouraged to spend as much time as possible when you go for the posters. So this is just an advertisement, 1 minute each, and they'll tell you what they're talking about.
Thanks. My poster is about charge pumping, Floquet states, and adiabatic pumping. What is charge pumping? Charge pumping is basically driving current in a transport channel, not by an application of bias, but by application of time-dependent potentials in the channel. So that is charge pumping. So I will discuss my work on charge pumping. I'll talk about Floquet states, and so this will be particularly in quantum wire. And I'll also discuss adiabatic pumping formula, and there is an interesting limit of this pumping formula, that is in an adiabatic limit, pumping can happen in perfectly reflecting scatterer also. So at every instant of time, the scattering channel is perfectly reflecting, but still over pumping one cycle, charge can be pumped from one side to the other, and such pumping can be realized on the edge of quantum spin Hall insulator. So I'll discuss that. You are welcome to take a look at my poster. Thanks.
Good morning. The question we address is there a discontinuous phase transition in the growth and shrinkage dynamics of microtubules? So microtubules are known to be very dynamic structures. It's been shown in experiments that single microtubules are associated with successive catastrophes and rescue events, which are characterized by rapid shrinkage in the length of microtubules followed by gradual rescue events. And there have been many theoretical models proposed to capture the behavior of microtubules. So we propose a modified random hydrolysis model, which capture the experimentally observed the length and time scales of catastrophes and rescues. From this model, what we observe is that the dynamics of microtubules, or the transition from the shrinkage to growth phase in microtubules, are associated with, have the characteristics of a discontinuous transition. So using the growth velocity of the filament as the order parameter, we find the coexistence of shrinkage and growth phase at the transition point, and a corresponding bimodality in the distribution of velocities, which we compare with the unimodal distribution from older models. We followed it with the mean field theory, which generate two linearly stable solutions and an unstable solution near the transition. And we propose an analogy of this transition with the liquid gas phase transition. Thank you.
Good morning. So I am Orgho from IMSC. I have done this work in collaboration with R. Rajesh from IMSC and Cole Ponautan and Oleg Jablonski from Warwick University. So I will describe our work on how we modeled aggregation and fragmentation of massive particles using the mean field Smoluchowski equation. The main result we derived was the distribution of the masses of the particles in some exact limit, and also for some asymptotic scaling forms of the mass distribution function. That's it.
Good morning. I am Orgho Das from Asian Bosch National Center for Basic Science. The question we have addressed that whether we can calculate the subsystem mass distribution of certain mass transport processes which exhibit correlations, and we have taken the mass chipping model and mass transport model, which are both continuous mass transport processes. We have calculated for them exact 2-point steady state calculation correlation, and also calculated the subsystem mass distribution using the additivity principle. I have done this work with Henry Chatterjee under the supervision of Dr. Purnabhrata Pradhan. That's it.
I'm from ICTS Kolkata, and I'm working with Arnab Dash. So, as we know, that quantum phase transition is characterized by the non-analytic behavior of some ground state properties at the critical point. So, we are trying to find that if the excited states have some signature of that critical point. So, we work with a non-integrable model and drive the apply an external pulse and so generate some out of equilibrium states and measure some quantities and see that there is a signature of the quantum phase transition in the properties of the out of equilibrium states. So please come to see my poster.
So the title of my poster is Spatiotemporal Correlations in Coulomb Clusters. This work is done under the supervision of Dr. Amit Ghoshal from IISER, Kolkata, and also in collaboration with Dr. Joydeep Chakraborty from Satyendranath Bose National Center for Basic Sciences, Kolkata. So the main focus of this work is to study the static and dynamical responses across thermal crossover of Coulomb interacting particles in two-dimensional confinements having symmetry and without symmetry. So the main results, some of the main results that I will be discussing in poster is that while static correlation fails to differentiate between these two confinements, but dynamic correlation is actually help in making clear distinction between two geometries. And also I'll show how ultrashort relaxation and some of the key features of glassy dynamics arises in the context of such confined geometries having no spatial symmetries. Thank you.
Hi, I'm Devmala Chakraborty from IISER, Kolkata. I've done this work under the supervision of Amit Ghoshal from IISER, Kolkata and Rajdeep Sen Sharma from TIFI, Mumbai. So I will be giving a poster on origin and consequences of disorder-induced inhomogeneities in cuprate superconductors. So we will see that for up to a moderate disorder, how strong correlations makes the superconductivity robust to disorder, and it hardly changes with disorder the off-diagonal long-range order or any other physical observables. But after a critical disorder, you go into a regime where the disorder can be considered to be strong, and the formalism is updated, and you will see that the superconductivity crashes down strongly by formation of non-superconducting islands. And we will see in the poster that how these two formalisms are very significantly different, and superconductivity can be seen as a part of two regimes where it is robust up to disorder of strength of the order of bandwidth, and it will crash down after that.
Abhishek Dar at ICTS here. And classical Szilard engine consists of a cylinder of certain volume V, and there's a single particle sitting which is equilibrated at temperature T. And at time T is equal to 0, a piston is introduced at V/2, and piston is moved quasi-statically. Piston is assumed to be of heavy mass, and the piston moves quasi-statically, thereby extracting work of kBT log 2, as I shown in the, I think the sign is wrong in the slide. So this is a classical Szilard engine. So we propose a microscopic model for this, where we consider even piston as a particle of finite mass, and it collides with the original particle elastically, whereas particle collides with the reservoir, which exchanges the velocity which is kept at temperature T. And we are interested in understanding different thermodynamic properties of this system. If you are interested, I'm happy to discuss with you some of our investigations. Thanks.
Good morning. My name is Harshini. I'm from IISER Pune, and I work in the field of quantum chaos, in which basically we look at quantum mechanical systems whose classical counterparts are chaotic. One of the things we look for signatures of chaos in these quantum mechanical systems. We look at the spacing distribution of the nearest neighbors of eigenvalues of the quantum spectra, and these correspond to some well-known results in random matrix theory. People have been trying to come up with a way to generalize this to higher order spacings. Recently, people have used something called the generalized Brody distribution, to study the kth nearest neighbors, and we look at some model quantum chaotic systems and see what results we get. The other thing that we do is that we separate the spectrum into states corresponding to localized, energy eigenvalues corresponding to localized states and those that are non-localized, or in a sense chaotic or random. And we see that these two kind of spacing distributions follow completely different class of statistics, and that's interesting to us. Thank you.
Hi. This is a biologically motivated problem. What we look for is how does confinement affects the kinetics of polymerization. So the first thing what we learn here is that when you have a physical barrier, it actually affects the kinetics. So you see it creates a depletion regime. So there is a slowing down of the dynamics as the separation between this filament and the wall decreases. This is the first thing we learned. Then we moved on to study how does the this effect affect the force generation in filament bundles. So we have an ultimate goal of looking at how force generation in microtubules like biological filament happens. Okay, thank you.
So, good morning. Good morning. The title of my poster is Kinetic of Vapor-Solid PhaseTransition. So phase transition is very common in nature. So there we see different types of phase transition like liquid, liquid, solid, solid, vapor, solid, vapor, solid, or and many others also. But here we will focus on the vapor-solid phase transition. So here we have quenched the system so far away from the critical line. So there the phase transition occurs where nucleus and growth. So as you have, as it's clear from the snapshots which I have presented here, so this disconnected morphology we have obtained, and inside the domain we observe such kind of crystallization, so which confirms this transition is vapor-solid phase transition. So in this work, we will our main focus on the domain morphology and growth of such kind of domains which are filament-like. So if you want to know more, please visit my poster.
Hello everybody. Today in my poster I am going to present some work on slow quench dynamic of exclusion process with hole dependent rates. So what I mean by slow quench is that when I am in disorder phase and I am slowly changing my control parameter and across the critical point and went to the order phase with, and I am changing the control parameter linearly in time with very slow rate 1 by tau. What happens in small time regime, my system is on an average in equilibrium because the quench time is comparable to the relaxation time of the system. And as it approached the critical point, the system went out of equilibrium, and because of that, across the critical point, I see the presence of excess number of domain walls or vortices depending on the systems from the disorder phase. So I'm looking this problem in one-dimensional non-equilibrium model, which is defined on a ring, and the particle has hardcore interactions, and particle hop to its empty nearest neighbors with the rate. So in this model, I'm asking the two most important questions. First, how does the dynamic of these systems, slow quench dynamics of this system depend on the non-equilibrium, because of non-equilibrium steady state changed with the quench tau, and there is a well-studied, this quench dynamic is well-studied in quantum and classical system via Kibble-Jerrick mechanism. So I'm asking the question, does it show any difference in behavior in comparison to the equilibrium systems? If you are interested in knowing more, please do come to my course.
Hello, I am Raj from IIT Madras. I work with Professor Sunil Kumar and Ramanujan Adhikari. The title of my poster is Colloidal Transport by Active Filaments. Here we propose a mechanism of colloidal transport by active filaments, where active filaments attach to the surface of a colloidal particle, and how a spontaneous hydrodynamic flow can transport a colloid we discuss here. Please do visit my poster.
Good morning, I am Rajkumar Sadhu from SN Bose, Kolkata, and I am going to present a poster on actin filament growing against a barrier with fluctuating shape. This actin filament is a component of cytoskeleton of eukaryotic cell, and they grow and generate significant amount of force, which is used by the cell in many important ways like cell movement, cell division. So this is a very important phenomenon, and there are studies where parallel actin filament is growing against some rigid barrier. Here we study the parallel actin filament which are growing on a fluctuating barrier and observe that there are few new results or new phenomena which are not observed earlier, like the shape of force velocity curve, which changes when we change the time scale associated with the filament and the barrier dynamics. Another thing is that the stall force, which is known to be only a function of number of filament, is also depends on the barrier size as well as the time scale of this filament and the barrier dynamics. And the roughness of the barrier also found to change on applying the external load. So I will explain these things in detail in my poster, so please visit my poster. Thank you.
Hello, I am Shankupal. I am from IISER Pune. The title of my poster is Quantum Manifestation of Classically Chaotic Non-KAM System. As I mentioned, I have considered a non-KAM system that is a kick particle in periodic potential barrier. This system shows an interesting properties, that is the classical mean energy grows subdivisively. And the mechanism that governs this subdivision is also interesting. And yeah. Here you can see that the classical mean energy is growing subdiffusively, while the quantum energy is saturating. That is, it is showing the localization phenomena. And this subdiffusion also we can control by varying the system parameters. So those who want to know in details, please come and visit my poster.
I am Subhadip Chakraborty from SN Bose Center, Kolkata. The title of my poster is Additivity Property and Non-Equilibrium Thermodynamics for Self-propelled Particles. Here we found the subsystem particle number distribution for active Brownian particle using additivity, and we verified it by simulation. Here is the plot. The lines are analytic and points are simulation. Thank you.
Hello, myself Shubhoto Dev. I am working under Dr. Shakuntala Chatterjee at SN Bose National Center. Okay, so I have calculated the first passage time of E. coli bacteria in a medium where the nutrient is diffusing. So by simulation, what we have found that the first passage time actually becomes minimum with the width of the nutrient. We have also calculated the first passage time analytically, and we have found a good agreement. Please come to see my posters. Thank you.
Hello, I am Archok, and I think Abhishek's talk was good advertisement of my poster anyway. So, there are this Markovian Quantum Master Equations which are often used to describe open systems, and there are two master equations that are generally used. One is Lindblad, another is Redfield, and there is this debate about which one is better. So we have compared it with the exact results, and we have shown that the Lindblad formalism may have serious pathologies which are completely cured by going to the Redfield formalism. So if you want more details, please come to my poster.
Hello, I am Aditya Kundu. This work is in collaboration with Abhishek there. So we are interested in this heat transport in classical 1D integrable models. So in the integrable in heat transport is usually studied numerically via two methods. One is by calculating the dynamical correlation functions and then relating it to Green-Cobo, and another is non-equilibrium simulations by attaching two heat paths. on both ends and calculating the transport properties. So in this work, we studied two integrable models. One is this harmonic, and the other is a Toda chain, which is a lattice with exponential interaction, and seen how what are the typical behaviors of these two chains. And we also comment on what fluctuating hydrodynamics can predict about, to what extent it can predict about these integral models. Thank you.
Hello, myself is Tanay Nag. I'm from IIT Kanpur. So here I will discuss the dynamics of decoherence, universal scaling of decoherence factor. So the main thing is that here I will consider a central spin model where a single qubit is coupled to the environment, which is driven across this critical point. So in the process of decoherence, the central spin will lose its coherence, and so in the vicinity of critical point, the decoherence factor falls in a power law fashion, like 1 minus chi f alpha 1 t plus alpha 2 t square. So first I will derive the scaling form of chi f alpha 1 alpha 2 by just dimensional analysis, and then numerically these are all been verified and analytically these are all been shown. So this is the main thing of my presentation. And next, away from the critical point, dt falls Gaussian. This shows a Gaussian-like behavior. So this is only dictated by alpha 2. So there are some anomaly regarding the scaling of alpha 2. So this anomaly has been settled successfully by our universal scaling form. Thank you.
Okay, everyone. Myself Pratik Malik. I'm from University of Calcutta, and I have been working this with my supervisor, Dr. Parangama Sen. So what I have done basically is I have considered the zero temperature quenching dynamics of Near-Never Ising model, and in my work I have studied the single spin flip Glauber dynamics to study all the three variants of the persistence probability. And in the 2D case, I have also studied the corresponding exit probability to just have a qualitative explanation of the nature of persistence. So what I have obtained is I have established the finite size scaling eligibility in the 1D case for the non-homogeneous systems. And in the 2D case, I have obtained a diverging time scale associated with the persistence probability for the minority spins, which has ultimately led to the discovery of a new exponent connecting time and length scales. Thank you.
Good morning. I'm Shori. The title of my poster is Large Compact Clusters and Fast Dynamics in Coupled Non-Equilibrium Systems. This work has been done in collaboration with Shakuntala Chatterjee, Mustansir Verma, and Shuklapal. So in our work, we mainly try to characterize ordering in a coupled non-equilibrium system where two species of particles, they get advected by a fluctuating landscape, and they also affect the landscape around their positions. So we tune the particle landscape coupling and obtain a phase diagram which shows novel non-equilibrium phases, which is valid for all particle densities, both in 1 and 2 dimensions. And the landscape induces complete phase separation between the two particle species, and the particles in turn affect the landscape such that the landscape develops 3 macroscopic regions under the influence of the particles, 2 with long-range order and a third without any. And the formation time scale and also the steady-state dynamics show algebraic time scale, which has never been seen earlier in systems with pure domains. Thank you.
Hello, myself Shraddha Sharma. I'm from IIT Kanpur, and I've done this work with Professor Amit Datta, Dr. Uma Divakaran, Professor Anatoly Polkovnikov, and Professor Sei Suzuki. I'll present dynamical phase transitions in which is a non-equilibrium real-time quantum phase transition. So I'll be talking about a phase transition which does not have a conventional order parameter or critical exponents, namely the dynamical phase transitions. And we'll show that these are the non-ellipticities occurring in real time for integrable and non-integrable systems. Thank you.
I'm from IISER Pune. This work is done in collaboration with Dr. Lakshmanarayan from IIT Madras. So some of the results I will present here. So we are in this poster, we are given a simple quantity which we are defined using the realignment and partial transpose, and both the operations are used in quantum entanglement. And we have studied this quantity in detail, and we have calculated it for various classes of states. And this quantity we have explicitly calculated for 2-qubit density matrices and compared it with the well-known measures of entanglement, namely concurrence and negativity. And we are given various inequalities on the concurrence and negativity in terms of R12 for all ranks of the 2-qubit density matrices. And not only that, we are given the unsought states which satisfies these bounds. And to know more details of this work, please visit my poster.
We now have movies.
I'm Abhiram from Mad Science. I'm working under Ramanujan. The work is actually motivated by a in vitro experiment where they put lots of microtubules and they let it in a nutrient solution. And what happens after some time, start beating very systematically. They start beating in very systematic fashion in a planar geometry. We also find from our theoretical model similar application, and where you will see that beating appears in a particular parameter range and it start oscillating in a plane, where you start with a 3D motion and from there you will get to a 2D planar beating kind of motion. And this work, further we also look at the other dynamics in detail, and that got featured into soft matter cover. So please drop by to my poster if you want to discuss more, and I'll be happy to discuss any more questions and others. Thank you.
Thank you. Is there anyone that we have missed? Or someone, anyone presenting a poster but whose slide or introduction was not here? This is the time to speak up. Okay, so if not, let's thank all the graduate students and postdocs for a very nice presentation and sticking to time as well. Thank you. So the next session, Sanjeev, is at 12, right? At 12, the session begins.